Zoom in a little bit. All right, good morning, everyone. I'm gonna stall for a little bit while I wait to make sure that things are going. And YouTube looks good, and Twitch is yelling at me about Nerf guns again. I don't know why Twitch thinks I want Nerf guns so much. I have never searched for Nerf guns. I don't think I've ever purchased a Nerf gun. This is poor marketing targeting. Sorry, little coffee sip. I'm going to try and keep the slurping to a minimum, but good morning. Today we are going to be reading a paper, and it's fairly hefty. So it's 9 pages, which is a long paper, and there's a lot in here. So I think it's probably going to take us a couple weeks, but I could be wrong. We might blaze right through this. Good morning, Fav1. Fav1? Could possibly be either. And the paper is, as you might deduce from the author affiliations, out of the Google Brain team. Fingerful says, what are we going to do today? Hopefully get a solid chunk of the way into this paper. This was the paper, so this came out in 2017 at NeurIPS, N-E-U-R-I-P-S, which is the new name of the NIPS conference. And it made a pretty big splash. There was definitely a lot of chit-chat about it. People tend to be excited by Google AI papers. And it was a fairly radically different model from what people were using at that point. And I really only know about this from the... So I've never really been a pure ML researcher. I've really been more on the NLP side of things. And when this came out in 2017, current state of the art in most NLP tasks was bidirectional LSTMs with attention, which is a specific flavor of recurrent neural nets. And this paper has no recurrence in it whatsoever. So it's a pretty strong departure from what people were doing. Well, that's not fair. People were also using convolutional neural nets for sequence to sequence things at this point. So that was sort of people were looking into it, but it hadn't really sort of like made a huge splash, at least in my particular friend network circle thing. And this paper made a much bigger splash, and the models proposed in this paper, they're called transformers, have had a fair amount of success in different tasks. There are a lot of tasks where bidirectional LSTM with attention is still sort of the most popular or best performing system. But transformers are doing really well, especially with machine translation. So these are sort of like current methods, even though this paper is almost 2 years old at this point. And the reason that I wanted to read this next is because, in addition to sort of like being a big sort of like sea change in the field, a lot of people are in dialogue with this paper. So if you are reading other papers in this area and they're more recent, they may talk about transformers, or they may talk about attention-only models, and that's sort of based on this paper. So I think it's an important paper to know about. I have skimmed it in the past. I don't have a deep, instinctual understanding of what's actually going on in these models. I think I have a fairly good idea how transformers work, but I could be wrong. So we'll find out together. More coffee. All right. So that's the background. Let's jump in. And this is the conference formerly known as NIPS paper, so it's probably going to be a little bit less focused on the tasks and more focused on just the architecture itself. So this is going to be fairly slow going, I'm imagining. Hello, Pratyush. Pratyush? If I say your name wrong, it's me. It's not because your name... There's nothing wrong with your name. Your name is beautiful. I just am bad at reading words. All right, abstract. The dominant sequence transduction models, I would probably call that sequence to sequence, where you have your input is a sequence and your output is a sequence. So this would be something like machine translation, where you have a sentence in one language that you put in, and out of that you get a sentence in a different language. So that's different from like a classification task where you have, something that you put in and the output is, the class that this belongs to. So a slightly different approach there, are based on complex, recurrent, or convolutional neural networks that include an encoder and a decoder. Okay, yeah, that sounds right to me. The best performing models also connect the encoder and decoder through an attention mechanism. Yes, that's still the case. People generally do that. And hopefully they will talk more about attention, because I kind of know how attention works, but I've never implemented one from scratch. So, and I should say this paper did not develop the concept of attention. That had been current in the field for quite a while. They just sort of got rid of everything but attention. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. Experiments on 2 machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 BLEU on the WMT 2014 English to German translation task. So BLEU is a metric for evaluating machine translation that gets also used in a lot of other places, and it's a bad metric, and I don't like it because you can get a very good BLEU score and get text that no human would accept. So that's my soapbox. We can talk more about BLEU if folks are interested. Actually, you know what? No, let's not talk about BLEU here. This is a blog post. This has been percolating for a while. So I'm going to tuck that away in the back of my mind and get back to there later. And then this is just a specific task that has a corpus that you train on, and then they have a particular test set. So like a Kaggle competition. Someone has linked the Jalama blog article, which I also really enjoyed. This is the link. It's very good. We might get there if I get blown out of the water by the paper. Ready to Learn says, what is the prerequisite knowledge for this session? Oof. I guess I'm sort of starting with the idea that you're familiar with a recurrent neural network. Maybe not like all the ins and outs, but you sort of know what they are. And I think we're going to be talking about them a little bit. So yeah, so not even that. Maybe sort of be familiar with what neural networks are kind of generally. And feel free to ask questions, and I can back down and back up and answer them to the best of my ability, or other folks in the chat might. People tend to be really helpful in these sessions, which I appreciate. Thanks, y'all. All right, so they get a good score on this particular English to German translation task. Improving over existing best results, they're claiming state of the art. That's pretty common in papers that get into NeurIPS, including ensembles by over 2 BLEU, so points on this scale. On the WMT 2014 English to French translation task, our model establishes a new single model state-of-the-art BLEU score of 41.0 after training for 3.8 days on 8 GPUs, a small fraction of the training costs of the best models from the literature. Yeah, which is, that's a long time. Like, if I were paying for that, I'd be like, that's too much time. But if you look at WaveNet, which trained for computer years, let's actually see, WaveNet training time. Oh, sorry, it went into a different, there we go. Okay, sorry. Well, I can't find it in the first 4 sound results. But anyway, WaveNet took a really long time to train, and that's the point that I'm making there. So that's not bad. And maybe we'll talk about it, but RNNs have specific properties that make training time slower for them, but they are very good for specific type of tasks. Okay, introduction. Recurrent neural networks, long short-term memory, LSTM, and gated recurrent neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation. If you guys were here for the last couple of reading sessions, you will know that a language model is a way of guessing what word will come next given an input string of words. So if I say I have an input string, it's time to feed I might have an output suggestion, things like cat, dog, hamster, whatever, baby maybe. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures. So the idea of an encoder-decoder is that you put your input string into the encoder, which is some sort of architecture, and then at least with recurrent architectures, there tends to be a single attention module in the middle here that links the encoder to the decoder. And then the decoder is what gives you the output from the information and the weights that you've gotten from the encoder. So this is part of the reason that you can avoid having sort of like word-to-word translation and just like transliteration. Instead, you have sort of like the sense of a sentence that comes through the encoder, and then you get that same sense of the sentence that comes through the decoder. More or less, kind of. And this is a... Oh, that's really nice. So here they're explicitly discussing the contribution of each of the authors. So the ones with stars on them had an equal contribution. So it looks like that's everybody, and different people did different things, and they give everybody appropriate credit, which is great. That's a really, really nice best practice for research papers. All right. Recurrent models typically factor computation along the symbol positions of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states, h sub t, as a function of the previous state, h sub t minus 1, at the input position t. So basically, if I am looking at, a specific word, I'm going to look at the previous words in sequence, and I have to compute each of the previous words in turn. So to look at word 5, I have to do word 1, then word 2, then word 3, then word 4, then word 5. That's what they're saying there. This inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths as memory constraints limit batching across examples. So because you need to do things in order, it makes it much harder to parallelize, because you can't do word 3 while you're doing word 1, because word 3 is dependent on word 1, if that sort of makes sense. And the memory constraints, I've read about this, and my eyes kind of glaze over when people start talking about hardware. I think it's like that you need more threads in your chip or something. I don't know. But basically, you have to use a pretty small batch size, and you can't really take advantage of GPUs when training recurrent structures. I mean, you can, but the sort of the boost you get is a little bit more limited because you have sort of dependencies in your graph that are time-based. Hopefully that makes sense. Recent work has achieved significant improvements in computational efficiency through factorization tricks and conditional computation. And I think there have been even more recent papers that are continuing to sort of chip away at this problem and make RNNs faster, because they are really good for a lot of stuff, while also improving model performance in the case of the latter. And these are just papers to go read. And this is because it's a NeurIPS paper. The citations are in the footnote style, so you don't see the name or the year of the citation, which drives me nuts. I hate it. I want to know who did the work and when, and I think that that's very important to put in the text, but we can argue about citation styles later. The fundamental constraint of sequential computation, however, remains. And I don't... Just like conceptually, I don't think that that's necessarily a problem. I mean, obviously it's a technical problem in terms of training and speeding up training. But people are generally using RNNs and LSTMs and gated RNNs for language tasks. And in language, things happen sequentially. So I know that we don't want our we don't necessarily want neural network architectures to be like good cognitive models, but the fact that you don't know, the next word I'm going to say until I say it has cognitive implications, and that, affects the structure of language and the way that we communicate, and there are inherent qualities of the system that have arisen because language is sequential. So I don't necessarily think that it is a problem to be doing the computation sequentially. So that's just sort of my little grandstanding on that particular subject. Attention models have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard to their distance in the input or output sequences. So attention basically allows you to upweight. So at a given step in the decoder, attention allows you to upweight and downweight things in the entire input sequence. So you're not just sort of upweighting the most recent things and then downweighting things that are further away. And this is really important for things like anaphore resolution or co-reference resolution. So if I say, I have a dog, his name is Bill, I need to know that his refers to the dog and not someone I was talking about earlier, like, I don't know, my friend. I can only come up with names that you wouldn't usually use his with here. Gerard. And then that co-reference resolution is figuring out that dog and his refer to the same thing. And an attention model in theory is going to do something like upweight dog and then downweight Gerard. Because it's trained. The attention model is trained. So if you get it wrong, you get a little, negative reward backpropagated. Shabam says, what resource do you prefer the most to study about attention? I don't know. Most of what I know about attention has come through watching talks, like where people are presenting papers, and that's maybe not the best way to learn about attention. Probably you should learn about attention like beforehand in a way that's designed to teach you about attention and not like the particular study you're finding out about. So yeah, I don't really have any good recommendations. If y'all do, please feel free to mention it in the comments. Or the chat. All right. In all but a few cases, attention mechanisms are used in conjunction with a recurrent network. And I am hoping that we will learn more about attention in this paper. And if not, that's upsetting. And we're going to have to go read another paper. Yeah, so it looks like 2 and 16 are the references that they're recommending. Scroll. So 2 is neural machine translation by jointly learning to align and translate from core by Dimitri Badnow et al. From 2014. And then 16 is the other one that they're recommending, Yoon Kim et al. Structured attention networks in ICLR. And just based on the paper titles, 2017, I'd probably recommend the Kim paper, just because I don't know what core is. And if I don't know what the conference is, probably I'm going to be a little bit more confused by what they're talking about, because it's not going to be my core, my core scholarly community. Whereas ICLR is, a conference that I know about and my friends go to. So you can see some social network effects right there. And we might actually read this if we don't get into attention in this paper. So it looks like it's out of Harvard, actually. That's interesting. I don't really think of them as a big NLP school, but maybe that's not fair. It's Me says, how to read research paper being undergraduate student. Just like jump in, I guess. I remember when I was reading research papers as an undergrad, I got like 5% of it, but then I got like 1 additional % with every other paper that I read. So it became more and more clear, and I understood it better and better. Personally, I think that I tend to get math, especially, let's see, we were in here. I tend to get math especially better from lecture than from reading. And that's just me. And also English is my native language, and a lot of math lectures are in English, so I don't have like a language barrier to struggle with, which I know for some people is absolutely a factor. Yeah. Ideally, you're going to get like structured guidance on how to read research papers in your coursework if you're a current student. And Akshay has given me different links, so let's open that up and pop that over. So this is Okay, so this is a discussion of this particular paper. Awesome, with code. Fabulous. So if we get to the attention and I'm completely stuck, we're gonna pop over there and check that up. Thank you for sharing that. Ashke. All right. In this work, we propose the transformer, a model, and all people have also called this a fully attentive network, FAN, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. Oh wow, this was a minute ago, huh? Okay, so basically they're saying our architecture has no recurrence, so it has no sort of like sequential dependencies. You don't have to train one before you train two when you're looking at the sequence. So you can train it more quickly, is their claim. I mean, you can train it more quickly. I think their claim is that this is a better model architecture. All right. The goal of reducing sequential computation also forms the foundation of the extended neural GPU, ByteNet, and Conv-S2S. I have not heard of the first two. The third one is convolutional sequence-to-sequence, all of which use convolutional neural networks as basic building block. I'm going to assume it's blocks. Computing hidden representations in parallel for all input and output positions. In these models, the number of operations required to relate signals from two arbitrary input or output positions grows in the distance between the positions. So if we have things that are very far apart, for example, for like the co-reference resolution I mentioned, if they're very distant, it's going to take more time to say that they're related. It's Me says, does every research paper include code in machine learning or deep learning, or they just add math behind it? It depends on the paper. They should. Ideally, they all will, and that's sort of like a pressure from the community is for more people to share their code. Yeah, if you're looking to implement a paper, I would recommend only implementing the ones that share their code, just because I think that's a better use of time. And a lot of research code is, it's very finely tuned, and for almost every application, you're not going to need super finely tuned code. You just need something that kind of works for what you're doing, or works better than what you had before. All right, blah, 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 blah. Grows in distance linearly for Conv-S2S and logarithmically for ByteNet, which is presumably why I have not heard of ByteNet. I don't know. I also am not super familiar with the state of the art in convolutions world, because generally that's used more for image processing, and I know next to nothing about image processing. I'm really much more in the NLP literature. This makes it more difficult to learn dependencies between distant positions. In the transformer, this is reduced to a constant number of operations. So no matter how far apart the things I'm looking at are in my input and my output text, it takes the same number of operations, presumably dependent on something in the model architecture. So if you've been studying for coding interviews and you're talking about time complexity, this is... Oh no, I have to remember the time complexity notation. Constant time, linear time, logarithmic time, and the n way of showing that it's early. That's my excuse. Albeit at the cost. So the trade-off is reduced effective resolution due to averaging attention-weighted positions. Okay, so you might be able to identify like 3 words next to each other and be like, it's one of these words, maybe. An effect we counteract with multi-head attention as described in section 3.2. I'm not entirely sure what this cost entails. I sort of told you what my guess is, but I need more information to sort of flesh out my idea there. Self-attention, sometimes called intra-attention, is an attention mechanism relating to different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, textual entailment, and learning text-independent separate sentence representations. So this would be, self-attention would be if I'm looking at a particular sentence for the purposes of a particular task, self-attention should upweight the parts of the sentence that are more relevant to that task and downweight the parts that are less relevant. So in like textual entailment, I'm trying to think of a really good example of textual entailment, and I can't. In reading comprehension, we might have something like, so this is like the SATs, if you've taken that. You have like a little reading passage, like, I don't know, Rachel was coding, it was early, she had coffee, and then the question would be like, was it the morning when Rachel was coding? And then you'd answer yes, no. And so for reading comprehension, you might upweight like early in that sentence, or maybe coffee, because you've learned a relationship between coffee and morning based on a input corpus that you're training on. And that's sort of the idea there. Okay. End-to-end memory networks are based on a recurrent attention mechanism instead of sequence-aligned recurrence, and have been shown to perform well on simple language question answering and language model tasks. Okay, so there's still recurrence where you look at the first item and then your output from this first item is an input to the second item in addition to input from the input data. So you're passing the hidden weight to each successive item is sort of the thing that happens in recurrent networks. But instead of that happening sort of at the embedding layer, it's happening at the attention layer, if I'm understanding. I'm also not super familiar with end-to-end memory networks, which is why I'm reading this paper. If I completely understood this this thing, I probably wouldn't be reading the paper. To the best of our knowledge, however, the transformer is the first transduction model. Transduction is just sequence to sequence. I don't know why they're saying transduction. Relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution. In the following section, we will describe the transformer, motivate self-attention, and discuss its advantages over models such as 14, 15, and 18. All right. It's Me says, can NLP and attention with some video package library be used to generate automatically caption in live YouTube video? So like a scene description, sort of like what's going on in the scene. There has been some work in that, and to my knowledge, which was kind of shaky, I think state of the art is multitask learning. So doing two things at once, one of which is describing the video, and the other one is, oh god, I'm trying to remember. It was at ACL like last year that I saw this paper. It was one of the best papers at ACL last year. So yes is the answer, and I'll try to find that paper. Remind me on some platform if I don't. Okay, so now we're actually going to learn about the transformer. And this is where it's going to start getting a little hairy, probably. And I may need to rely on this code example. All right. Oh, okay, so this is actually just the text of the paper plus the additional code. All right, that's helpful. I'm actually going to zoom in a little bit as we come in here. Shoop, shoop. Nope. Yep. All right. Model architecture. Getting into it. Most competitive neural sequence transduction models just say sequence to sequence. I'm sure they have a very good reason for choosing this particular way of discussing it. Have an encoder-decoder structure. Here, the encoder maps an input sequence of symbol representations, x sub 1 to x sub n, to a sequence of continuous representations, z sub 1 to z sub n. So basically you have your words or whatever, and then you end up with a vector that is summarizing in some sense the information in whatever it is that you're putting in. Given z, so this vector, the decoder then generates an output sequence y1 to y sub m. Notice that it does not have to be the same dimensions as the input sequence, of symbols one element at a time. So we sort of encode everything, and then we go through and we say, all right, first output, second output, third output. At each step, the model is auto-regressive, consuming the previously generated symbols as additional input when generating the next. And so in our output, we've outputted like the first one in our output. So, I don't know, the first word in our translated sentence, and then the second word in our translated sentence depends on this representation that we've been passed, which is sometimes called a thought vector. I don't think it necessarily represents human thought in any way. And it's also dependent on the previous word that we generated. Google show, attend, and tell was one of the caption images. So there must be modifications on that for video frames as well. Is this? So this is from 2015, attention-based model that automatically learns to describe the content of images. We describe how we can train this model in a deterministic manner using backprop and maximizing variational lower bound. Blah, blah, blah. They use the Flickr data sets. Okay, cool. I've definitely heard of this paper, but I have not read it. But yes, there definitely is work on video captioning. But as I think I mentioned, I'm not super into what people are doing in the image processing world. So that paper might be a good place to start. And you could also look at things that have cited it. Sorry. Yeah, things that have cited it, which is a lot. All right, where were we? Model architecture. Okay, so we talked about sort of like the general encoder-decoder structure. The transformer follows this overall architecture using stacked self-attention and pointwise fully connected layers for both the encoder and the decoder, shown in the left and right halves of figure 1 respectively. Let's look at figure 1. All right. So we still have, it looks like, does this have a, no, this is all that we, this is all that we get in terms of figure. So the thing that they want us to get from this is that it has stacked self-attention. So, all right, so these are the inputs. So this is where our input goes in, and then we have input embeddings. So sort of a semantic representation of our input words. I'm just going to say words because we're working on machine translation. And then there is positional encoding. I don't know what that is. Oh, we'll learn about that. Actually, maybe scrolling up. Okay, well, we don't actually learn about that until way later down, so let's just ignore that for now and know that that's something to come back to. And then we have multi-headed attention, which I know is something that they've introduced in this paper, and I don't know what that is. So this is maybe the self-attention, so where in the input sequence we upweight things that we think are important based on feedback and downweight things that we think are less important in the sequence. And then we add and normalize. Okay, and then we have a feed forward network in here. So sort of like your vanilla MLP architecture in this little bit. Multi-layer perceptron, sorry. And then we have more adding and normalizing. So this whole thing is the what I would call the encoder. And then this would be more like the decoder. So you have the embeddings. So these are going to be embeddings based on the outputs. Shifted right. So it would be like the next output, I guess. So I'm not entirely sure if this is getting in a whole sequence and giving out a whole sequence, or getting in a whole sequence and getting in the next item, and then the next item, and then the next item. Or maybe there's one of these for each of the output items, but I don't know how you'd know a priori how many output items to have. I'm real confused, y'all. Let's see if, well, okay, let's finish going. So same thing here as here, but the inputs are also from the output embeddings that have gone through this masked multi-head attention. I don't know what a multi-head attention is, so there's that. And then we have the same sort of like structures here, simple feed forward network. There's this add and norm layers. And then finally you have a linear model and then softmax. So maybe this is sort of like the entire space. So maybe this is the vocabulary and we are doing softmax over the vocabulary, but I don't know then how you know which word is which. So if I have just sort of like my input words as just as a bag of words, and then I have my entire possible output vocabulary as a huge bag of words, and then I use my input embeddings to suggest that these words are important, I pick out, the things that I think are most relevant, and then I take softmax. Well, that would give you one usually. Maybe that's what the positional encoding does? Well, I don't know what's going on here. Let's keep reading and see if that helps. Okay. Encoder and decoder stacks. I think we should read the whole model architecture and then come back to that figure and see if it becomes clearer. The encoder is composed... Oh my gosh, y'all, I just realized. So I'm from the South and I have what's known as the pin-pen merger in some context, which is where the vowel sound in the word pin and the vowel sound in the word pen are smushed. And I just realized that I have it in encoder. And I suppose some people might say encoder, but I definitely say encoder. Spam says, so we are clear, NX in the figure means the same block is stacked multiple times. Okay, so there's like multiple layers of this. So this is like one layer of a layer cake. It's me says, is it bad as a data science to use transfer learning on my every side project? It seems sufficient. Somebody's trained the network, you might as well use it. Okay. Each encoder is composed of a stack of n equals 6 individual layers. Okay, so we have 6 of these sort of input cakes. Each layer has 2 sublayers. So these are the sublayers, the multi-headed attention and the feed-forward network. The first is a multi-head self-attention mechanism, and the second is a simple, position-wise, fully connected feed-forward neural network. Okay. So we have as the inputs to here, where word 1 is input node 1, word 2 is input node 2, word 3 is input node 3, and then we have the fully connected feed-forward neural network architecture. Okay, that makes sense, but I still don't know what the multi-headed attention thing is. We employ a residual connection, 10, around each of the 2 sublayers, followed by layer normalization. We employ a residual connection around each of the 2 sublayers. So the input here, we feed back into this layer. So we sort of have the transformed version with multi-head attention, and then we have the untransformed version as well. Maybe that keeps neurons from dying? I don't know. That is, the output of each sublayer is layer norm x plus sublayer x, where sublayer x is the function implemented by the sublayer itself. Okay, yeah, so we have the input string that we've transformed into an embedding, and then we have the sort of like sub-layer multi-headed attention output, and then we take the normalization of both of those. Okay, so the adding the norming step is taking our vector that we're inputting to this, and then the output of this, and you sort of take the average of them. Okay, that makes sense. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension d submodel equals 512. All sublayers in the model, as well as the embedding layer. Okay, so everything has a dimension of 512, so you can sort of like stack them nicely. So that's just like making sure that if you're using like Legos to build something, you choose Legos that are all of the same length so that they can go together nicely and don't have like overhangs and bits you have to chop off. You don't chop bits off Legos. Probably you don't chop bits off Legos. Okay. So that makes a sense to me, but I don't know what the multi-head attention is. Okay, so I don't think they want us to understand this right now. I think they just want us to know where it is in their architecture. So if that's the goal of the authors right now, big old checkaroonie, I know where it is in the architecture. I don't know what it does. It attends. It upweights things that are important and downweights things that are not important. Why are there 3 of them? I don't know. We'll figure it out together. All right. Decoder. So this half is the encoder, and this is actually one stack of the cake, and we've got one layer of the cake, and we've got multiple layers. And we're probably going to have the same thing on this side as well. Yep, 6 identical layers. In addition to the 2 sub-layers in each encoder layer, so these ones that are just the same as they are over here, except we have inputs from the output and also from the input. The decoder inserts a 3rd sub-layer, which performs multi-head attention over the output of the encoder stack. Okay, so these are actually in a row, and the input here is going to be the output of, so if we're on n sub 2, the input to n sub 2 is going to be the output of n sub 1. So you do have sort of like a sequential model, kind of. Subash says, can BERT paper be done next? Yeah, sure. Fun fact, it's not fun, that I just learned about the BERT paper is that it's never actually been published. It's still just an archive paper. But yeah, no, we can do BERT next for sure. I'll put it in the queue. Ugh. Okay. Which performs multi-head attention over the output of the encoder stack. Okay, so we have multi-head attention just on the previous output, and then we also do multi-head attention including information from the input. Okay, that makes sense to me. Where were we? Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. So we have this sort of like little pipeline that ignores all of the attention and feed forward networks, which I guess is sort of like a little bit of insurance against having a network that just gets really weird for some reason. Maybe a lot of the cells die and you get a lot of zeros out, but as long as you're norming on your input as well, then you're not going to completely, kill your entire stack by having one weird cell. So that seems like sort of like an insurance policy to me. Shrug. Hamish says, am I right in thinking the arrows avoiding the multi-head attention layers are skipped connections like in ResNet? I'm not super familiar with ResNet, but yes, maybe? I don't know. Maybe someone who knows ResNet better can help out. ResNet's an image thing, right? Let me just say a little boop. Actually, that probably will get me to something. Oh, yeah, that's an image thing. Yeah, maybe someone who is more familiar with ResNet can answer that. All right. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. Okay, that makes sense to me. So, what this means is that when we're doing self-attention, if I'm trying to guess the next word, I can't look at the next word. So I'm only moving forward in time when I'm looking at the embedding. But I can do that when I'm looking at the output, but I can do that in the input. I can look at things that come next to figure out what should be important now. which I guess makes sense because our time point here is that the input has already been created and we're generating the output. So it makes sense to be able to look at the full input. Okay, I like that. That makes sense. That's intuitive to me. This masking, oh, that's what the masking is. Gotcha. So the masking is that you can only attend to things that are the current state or previous to the current state. You can't attend to the future, which makes sense. When I first saw the title, I thought it will tell about physical attention needed to read the paper. Yeah, I have definitely read worse deep learning papers. I would say that this is fairly well written. And not just because it's potentially my coworker that I might run into. I mean, it is my coworker, and I guess I might run into him. He's probably in Mountain View. I don't know. Who wrote this? Coworkers, multiple authors on this paper. Okay. The masking, combined with the fact that the output embeddings are offset by one position, ensures the prediction for position I can only depend on known outputs at position less than I. So shifted right. I don't get the shifting. I don't understand what that does. So I am, okay, so I'm at time point T in my output. Things have been shifted right. And I don't know if that means that the string has been shifted right. The outputs have been shifted right. Okay, so the input string has been shifted one section right, let's say. So if I was at T, now T is outside of my current span. So I can only see T minus 1 through T minus N. So I can't attend on the current output. Okay. That makes sense to me. I think the shifted right means T plus 1 relative to the encoder at T. Yes, I think that's right, Hamish. Also, there's like a little bit of a lag, so you probably were typing that as I was saying that. Okay. This kind of makes sense. I'm grokking it, to use a word that I strongly associate with Linux uncles. Not that there's anything wrong with Linux uncles, but it's definitely like a genre of person. Okay. An attention function can be described as mapping a query and a set of key value pairs to an output where the query, keys, values, and output are all vectors. What? An attention function can be described as mapping a query, okay, so that's a vector, and a set of key value pairs, those are both vectors, to an output where the query, keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. I'm gonna need some more coffee. All right, let me just take a sip. Sorry, I know a lot of people have dysphonia and hate the sound of people chewing or drinking, and hopefully this isn't setting anybody off, and it is. I apologize. Okay. The output is the weighted sum of the values, where the weight assigned to each value, I keep reading this like it's going to make more sense on the 8th pass, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. Okay, so you have, Jer says something embedding multiplication. I think let's see, this structured attention networks. Do you have a better picture? Neural machine translation. So this is recurrent here. So you see how there's a dependency between each of these, and this would be the output attention layer. So this is sort of the normal state of the art in 2017. attention distribution where context vector what. Okay. So there's sort of like a weight associated with each of these. So if this, okay, so the weight would be the output. Okay, let's see. Maybe there's something more helpful here. Help me with the attention. ATTENTION. There we go. Whoop. We call our particular attention, is this part of the paper? Yes, this is part of the paper. Figure 2. Okay, so there's a figure. Scale dot product attention on the left, and on the right is multi-headed contention consists of several attention layers running in parallel. Okay. So this is the query, this is the key, this is the value, this is the output. I don't understand why there's Sabam says this attention is different from other attention techniques I read. Maybe we look at the J. Alamar blog. That is a good idea. Thank you. I forgot I had that open. I don't understand why you need a query and a key. Basically, there's additional self-attention, encoding. Here's the feed-forward recurrent network. Self-attention at a high level. Self-attention is only going to be in the encoder, though. This might still help us with the attention part. Okay. So this is a sentence. What does it in the sentence refer to? So the sentence is the animal... Sorry, so we're now reading the J. Alamar Illustrated Transformer blog post. And there's an example sentence, the animal didn't cross the street because it was too tired. And it's a co-reference resolution, so is it referring to street or animal? In this case, animal, because streets can't be tired. So the model processes each word, each position in the input sentence. Self-attention allows it to look at other positions in the input sequence for clues that can help lead to a better encoding for this word. Okay. If you're familiar with RNNs, think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words / vectors it has processed with the current one it's processing. Self-attention is a method the transformer uses to make the understanding, quote unquote, of other relevant words into the one we're currently processing. Okay, so you can see that there's sort of like lines with weights, and the animal has a higher weight than street does. Here we go. Okay. Self-attention in detail. Let's first look at how to calculate self-attention using vectors, then proceed to look at how it's actually implemented using matrices. The first step in calculating self-attention is to create 3 vectors from each of the encoding input vectors. In this case, the embedding of each word. So for each word, we create a query vector, a key vector, and a value vector. These vectors are created by multiplying the embedding by 3 matrices that we trained during the training process. I still don't know why we have 3. Okay, so we have 3 matrices that we've trained. So we have a matrix of all queries, we have a matrix of all keys, and we have a matrix of all values. For our vocabulary, I'm assuming, so it would be like, sort of like training, so like how you would train both an embedding layer and a language model at the same time. In addition to the embedding layer, we're also training queries, keys, and values. I still don't know why there's 3. It's Me says, where to go if we didn't understand anything on research paper? Ugh. YouTube, maybe? A lot of times, if there's a research paper in ML, it will have had a talk and people will share the talk online. I generally find talks much more helpful than just the papers themselves. Or I guess Stack Overflow. Stack Overflow tends to be pretty good if you have a specific question. All right. Multiply. The new vectors are smaller in dimension than the embedding vector. Their dimension is 764, while the embedding and encoder input vectors have dimensionality of 512. They don't have to be smaller. This is an architecture choice to make the computation of multi-headed attention mostly constant. Okay, so remember how no matter how far apart the things that we're looking at in this model, it takes the same amount of time to look at all of them. What are the query, key, and value vectors? Thank you. This is the thing I am not getting, and I don't understand why there's 3 of them. They're abstractions that are useful for calculating and thinking about attention. Are they? Once you proceed, I'm sure they are. I'm just being snarky because I'm confused and frustrated, and I'm like a little, I don't know, trapped raccoon. Once you proceed with reading how attention is calculated below, you'll know pretty much all you need to know about the role each of these vectors plays. I'm excited by this premise. I do want to understand the role here. The second step in calculating self-attention is to calculate a score. So the first step was creating vectors from the matrices that we've trained earlier. So we just like take a slice. I guess we have 3 because we're taking specific slices. Okay, calculate a score. We're calculating the self-attention for the first word in the example, thinking. So our example here is a 2-word phrase, thinking machines. We need to score each word of the input sentence against this word. Okay. We need to score each word of the input sentence against this word. So this is the actual thing that is what I have been thinking about attention, where for a word X, I have a weight associated with each other word in the sentence, or in the input. The score determines how much focus to place on other parts of the input sentence as we encode the word at a certain position. Okay, so this is what I think of as attention in my head. And the reason that we have multiple matrices is to do this computation. The score is calculated by taking the dot product of the query vector, which is a slice of a matrix we've trained, with the key vector of the representative word we're scoring. So keys are associated with specific words in it must be in our input. It can't be in our vocabulary because the dimensions are only 64. And I guarantee you're not doing machine translation with a vocabulary of 64. I say that. Maybe if you're working with like a fictional language, you might have a vocabulary of 64 because those are all of the words that we have. Okay. So if we're processing the self-attention for the word in position 1, the first score will be the dot product of Q1 and K1. So the query and the key for value 1. And the key value is going to depend on the word, and the query value is also going to depend on the word. The second score would be the dot product of Q1 and Q2. So here we can see that the dot product is higher for thinking on itself than it is for machines. The third and fourth steps are to divide the scores by 8, the square root of the dimension of the key vectors used in the paper, 64. This leads to having more stable gradients. Oh, okay, so this is just like a little trick to help out. There could be other possible values here, but this is the default. Then, passing the result through a softmax operation. Softmax normalizes the score so they're all positive and add up to 1. Okay, so we have, I don't know what have we used the values? We have not used the values. Okay, so we have this query, this key, these are both matrices. Each one is associated with a specific word. These are both vectors taken from matrices that we've trained. And they're taken from the same matrix. So this is sort of like, I don't know that we should call them queries and keys. I might call them like matrix 1 and matrix 2. That's not very helpful. So we just take the slice associated with each word with each of these matrices. We take the dot product. We take the softmax. So we have sort of like percentage of attention, except it's out of 1, so it's the one that starts with P that's not percentage. Dia says, how could attention mechanism be used to build OCR model to train it, for example, on COCO dataset? That's a good question that I don't know the answer to. Yeah, if someone else knows, maybe you can help out. I would probably search for a paper, maybe attention, OCR, Coco, or even on GitHub, just to see if someone has released code for that particular thing. And then you don't have to write it. You can, well, you don't have to start from scratch. You can try their model, or on Kaggle. We have code on Kaggle as well. Okay, so here we have sort of like the percentage of attention on each word based on these two slices from these two matrices, which are trained and have a dimension of 64. So how do we know which part of the query and the key to take? Maybe there's two matrices because so this is the same index. I don't know how we know which part of the matrix is the query for a specific word, because we don't have as many spots. We don't have as many like columns or rows in the matrix as we have words in our vocabulary. So maybe we're training a separate attention matrix for each input. But would that mean that you can't have queries, you can't have inputs of longer than 64? Query and a value projection of each word name. Okay, multiplying. Oh, I can't read. That's the problem. So the way that we get this matrix is that we are multiplying our embedding by this matrix, and we're multiplying our embedding by this matrix. So these are projections of that matrix. Okay, that makes so much more sense. So it's not like a lookup table. It's actually just like something that's uninterpretable at that point. Okay. I get it. So the way that we get both our queries and our keys is by multiplying our embedding matrix by this little guy that we've been training. Both of the little guys that we've been training. I don't think that there's any difference between the query and the key. I think. WQ dimension, Swam says, is length of word embedding times 64. Gotcha. That makes sense to me. Okay. Yeah, that makes sense to me. So it's sort of like an extra embedding that we're training, where it's the dimension of the embeddings by 64 rather than 512. So you could have it as long as you want. It just needs to be the same. One of the dimensions needs to be the same as your input dimension, your input embedding dimension. Gotcha. Very helpful. Thank you. I still don't know what we're doing with the values, and I still don't know why there's two of them. Presumably because it works better. All right. So we have this sort of like attention, little thingadoogle here, weight associated with them. Dividing by 8 is just a normalization, apparently. And 8 could be any number here. This isn't, specified by the model. For gradient stability. All right. The softmax or blah, 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 blah. Clearly the word at this position will have the highest softmax score because a word should always be most relevant to itself. But sometimes it's useful to attend to another word that is relevant to the current word. Okay. So far, so good. I think I'm getting this. The fifth step is to multiply each value vector by the softmax score in preparation to sum them up. The intuition here is to keep intact the values of the words we want to focus out and drown out irrelevant words by multiplying them by tiny numbers. Okay, so the value... So the value should be higher for the current word? Oh, wait, okay. So each value vector by the softmax score. The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words by multiplying. Oh, okay. So because we are multiplying this value, which is also based on yet another matrix that we are training, which is the length of the embedding by the 64 in this case. So these should all be 64 long if we're representing the architecture in the paper. Then the value is just sort of a placeholder, and then we multiply that by the weight that we have calculated earlier. So this weight is going to be very small because we gave a very low attention number to machines, and we gave a much higher number to thinking. All right, I'm picking up what's being put down here. The sixth step is to sum up the weighted values, the weighted value vectors. This produces the output of the self-attention layer at this position for the first word. So we would only have, so if we're basing it on this example, I think our output here would actually be 2. Some of the weighted value vectors. Oh no, it's the sum. So we add this vector to this vector. So I think at this point this is also going to be uninterpretable because it's not that. So so in the attention calculation, this softmax of the dot product of the first the query and key, quote unquote, matrices is fairly interpretable. And then we downweight the effect of the low weighted words. And then we add these together. And at this point, I think this is going to be fairly hard to interpret. Like if I just showed you this vector, I don't think it would, because it's not clear which part of the vector relates to thinking, which part of the vector relates to machines. We can get that information out of the model, but it's not going to be apparent from this vector. And this would also be 1 by 64. Okay. This is making sense now. I get it. The resulting vector is one that we can send along to the feed-forward neural network. In the actual implementation, however, this calculation is done in matrix form for faster processing. So let's look at that now that we've an intuition of the calculation at the word level. So here, this is our embedding matrix. This is our weight. This is our query matrix that we've trained. And then Q is all of the words in our input. And then we do the same thing with K, all of the words in our input. We multiply their embeddings by the weight matrix that we've trained, and then we do the same thing for the values. And then we just sort of do the same process that we did, but instead of doing each layer and each word independently, we do them as matrices. Okay. So that's what's going on here. Multi-head attention we haven't talked to yet. So we read 3 pages in an hour and 10 minutes. Math is hard. No, this is, I think it's just very dense because of size limitations. So it's super helpful. Again, this blog post that we've been looking at with the extremely helpful pictures. Thanks for the link. Was it Sabam who posted the link in here a little bit earlier? Yeah, it was Sabam. Thank you. Is the Illustrated Transformer by J. Alamar, and it's jalamar.github.io/illustrated-transformer is the blog post if you're interested in reading it. So at this rate, it's going to take us a month to read this paper. But I think so far, this is making pretty good sense to me, except we don't know what multi-headed means, and I'm not entirely sure what the positional encoding bit does. But the rest of it, I think, more or less, I'm getting, which is good. That's progress. For sure, that's progress. All right, so I'm going to call it now because I've got other stuff to do today, I guess. Thanks for joining me, guys. I hope this was educational. I like learning how to read papers is just like a learned skill. You got to practice it like everything else, and I hope it is helpful to watch someone else read a paper and just like be super confused and work through that. And hopefully you guys are also building your own understanding of this particular model architecture. And I will see you. I will be streaming this Friday. I'm going to continue working on that thing that I was doing, which was recurrent neural networks in R with TensorFlow for sarcasm detection. That's right. So I might do some thinking. I might do some thinking around what I might do there to have like a nice baseline to compare our neural network to. So Mom says, understanding papers gets faster from here. Yeah, for sure. You get faster the more you do it. And I'm gonna sign off for now. Thanks for joining, and I will talk to you guys on Friday if you tune in then, or next Wednesday if Fridays don't work for you. Bye.